Hi, my name is Khairisa Muhammad Nizal. My entry number is P112410002 and I will be solving question 1A and 1B. We have a metal rod heated at one end with temperature distribution. The temperature along this rod is T of x equal 3 exponent to the power of 2x, where x is between 0 and 1 inclusive. The rod is insulated along its side. First, let's construct the half-range Fourier cosine series. For a half-range cosine series on 0 less than x less than L with L equals to 1, the general form is, I will show on my tablet, Ts equal to A naught over 2 plus summation n equal to 1 to infinity an cos n pi x. Whereas for A naught equal to 2 times the integral from 0 to 1 dx dx. For an equal to 2 times the integral from 0 to 1 dx cosine n pi x dx. Okay, now let's compute A naught first. The formula for A naught equal to 2 times the integral from 0 to 1 of dx dx. This is the formula of A naught. So, now we substitute dx equal to 3 exponent power of 2x. So, we get 2 times integral 0 from 1, 3 exponent power of 2x dx. First, I will take the constant 3 outside the integral. So, 2 times 3 given us 6. So, we have 6 times the integral from 0 to the 1 of exponent to the power of 2x dx. Now, we integrate exponent to the power of 2x. The integral of exponent to the power of 2x is exponent to the power of 2x over 2. And we evaluate this from 0 to 1. At upper limit, x equal to 1, we get exponent to the power of 2 over 2. At the lower limit, x equal to 0, we get exponent to the power of 0 over 2. Exponent power of 0 equal to 1, so that 1 over 2. And then we have 6 times open bracket exponent squared over 2 minus 1 over 2 close bracket. Now we simplify. The 1 over 2 and exponent squared over 2 have the same denominator. So we combine them to get exponent squared minus 1 all over 2. 6 divided by 2 equal to 3. So we get 3 times open bracket exponent squared minus 1 close bracket. So A naught equal to 3 times exponent squared minus 1. Remember, in the cosine series, we need A naught over 2, so we divided by 2, giving us 3 times exponent squared minus 1 over 2. This is our constant term. It represents the average temperature along the rod. To compute AN, we use tabular method. We set up a table with alternating sign, differentiate exponent to the power of 2x, integrate cosine n pi x. Following the pattern, we get a loop. The integral appears again on the right side. This is the tabular method that I calculate. We solve for I, giving us exponent to the power of 2x, open bracket, n pi x plus 2 cosine n pi x, close bracket, over n squared by squared plus 4. Evaluating from 0 to 1, At x equal to 1, we get 2 exponent squared negative 1 to the power of n. At x equals 0, we get 2. Subtract, then multiply by the 6 outside. So, an equal 12 times exponent power of 2 negative 1 to the power of n minus 1 over 4 plus n squared pi squared. For part B, we approximate the temperature using the first three non-zero terms. For our formula, for an, we substitute n equal to 1, 2 and 3. For n equal 1, we get 1 equal negative 12 times exponent's power of 2 plus 1 over 4 plus pi squared. For n equal to 2, we get a2 equal 12 times exponent power of 2 minus 1 over 4 plus 4 pi squared. For n equal 3, we get a3 equal negative 12 times exponent's power of 2 plus 1 over 4 plus 9 pi squared. So, the three terms approximation is the constant term plus a1 cosine pi x plus a2 cosine 2 pi x plus a3 cosine 3 pi x. This is our practical estimate for the temperature distribution along the road. For the next question, I will pass to my friend.
Hi, my name is Rishi Naidu, B11252510121. Today the question I do is question 1, and the question I'll be explaining is C, D and E. For part C, Y cosine series for insulated boundaries. When a rod is terminally insulated at its ends, it means no heat can leave through those boundaries. According to Fourier's law of heat conduction, zero heat flow translates mathematically to a zero temperature gradient. In other words, the derivatives of temperature with respect to distance must be zero at both ends. Partial t over partial x equals to 0 at x equals to 0 and x equals to L. The terms of half-range cosine series are built using cos n pi x over L. If we take the derivative of these terms, we get sine function negative n pi over L, sine n pi x over L. Because sine 0 equals to 0 and sine n pi equals to 0, the cosine series naturally and automatically satisfy the insulated boundary condition without any adjustment. That's why it's a perfect match. Alright, let's tackle part D, where we need to find the half-range sine series expansion for our temperature function t bracket x bracket equals to t exponential 2x over the length L equals to 1. Our goal here is to rewrite this exponential temperature distribution using only sine wave. The general formula we use is Tx equals to summation bn sine bracket n pi x bracket. To make things happen, our mission is to find coefficient of bn. We do this by setting up a specific integration formula. Bn equals to 2 integration t exponential 2e sine n pi x dx. Let's clean up that first. We can pull the constant out of the front, which gives us bn equals to 6 integration e 2x exponential 2x sine n pi x dx. The number 6 get because 2 times with 3 we get 6. Now integrating an exponential multiplied by a sine function can look intimidating. We can easily solve it using standard calculus integration identity. The calculation will be exponential 2x over 4 plus n square times with pi square bracket 2 sine n pi x minus n pi cos bracket n pi x bracket integration 1 0. Next, we need to evaluate this expression at our upper limit of 1 and our lower limit of 0. When we plug in x equals to 1, the sine term becomes sine n pi, which is always 0. The cosine term becomes cos n pi, which is simplified into negative 1 power of n. When we plug in x equals to 0, sine 0 is 0 and cos 0 is 1. And we subtract the lower limit from the upper limit and multiply by our side constant of 6. Everything condensed beautifully into our final value of bn. Though the final calculation will be bn equals to 6n pi bracket 1 minus negative 1 power of n exponential 2 over 4 plus n square over pi square. Finally, we just substitute this bn back into our original series format, giving us complete half-range Fourier sine series explanation equal to tx equals to summation 6n pi bracket n 1 minus negative 1 power of n exponential 2 over 4 plus n square times pi square times with sine n pi x, and that completes the part D. Let's go for question E. Explain when the sine series is more appropriate in mechanical system. A half-range Fourier sine series is chosen when the system enforces zero-value concentrates as boundaries. Thermal system, when both ends of a rod or plate are held fixed at a constant reference temperature of 0, such as being in contact with ice baths and constant temperature heat sinks. Structural system, when analyzing the displacement of a vibration of a string of a beam that is fixed or pinned at both ends.
Hi and Assalamualaikum. My name is Muhammad Harith Irfan bin Muhammad Shukran and my metric number is B11 25 177. Okay, for question 2, part A, we need to formulate the boundary condition and initial condition of the vibrating string. Since the string is fit at both ends, the displacement at both ends is always 0. Therefore, the boundary condition U0t equal to 0 and U30t equal to 0. Next, for the initial displacement, the point located 10 cm from NA is pulled up by 3 cm. This creates two straight line segments. For the first section, from 0 to 10 cm, the gradient is 3 over 10. So the equation is U at 0 equal to 3 over 10 x. How I get 3 over 10? The value 3 over 10 comes from the gradient of the first straight line. The string rises 3 cm over a horizontal distance. A horizontal distance of 10 cm. So using the gradient formula, rise over run, we get 3 over 10. Since the line passes through the origin 0 0, the equation becomes u at 0 equal to 3 over 10x. For the second section, from 10 to 30 cm, the gradient is minus 3 over 20, giving the equation u at 0 equal to minus 3 over 20x plus 4.5. How I get minus 3 over 20x plus 4.5? The value 4.5 is the y-intercept of the second line. After finding the gradient, minus 3 over 20, I substitute the point 10 3 into the equation. Y equal to mx plus c. Solving for c give 4.5, so the second equation become u at 0 equal to minus 3 over 20x plus 4.5. Finally, because the string is released from rest, its initial velocity is 0, therefore ut at 0 equal to 0. These are the required boundary and initial condition for the vibrating string problem. For question 2, part B, I use the method of separation of variable to solve the wave equation utt equal to 9uxx. First, I assume the solution is uxt equal to xxtt. Then I substitute this into the wave equation. After dividing by xxtt, I separate the variable to obtain t double prime over 90 equal to x double prime over x equal to p, where the p is the separation constant. Next, I apply the boundary condition since both ends of the string are fixed. U0t equal to 0, U30t equal to 0. This gives x0 equal to 0, x30 equal to 0. Then I consider different values of the separation constant. For case 1, when p equal to 0, the solution is xx equal to a plus bx. Applying the boundary condition give a equal to 0 and b equal to 0. Therefore, the only solution is the trivial solution xx equal to 0. So this case is omitted. For case 2, when p more than 0, the solution is xx equal to a e the power of lambda x plus b e the power of minus lambda x. Applying the boundary condition again result in a equal to 0 and b equal to 0. This also give only the trivial solution, so case 2 is omitted.
Assalamualaikum warahmatullahi wabarakatuh. My name is As'ad bin Ahmad Mukhtar. My matrix number is B1125-10110. I will continue question 2B, case 3. In case 3, we assume P is less than 0, so we write P equals to negative lambda x squared. And the spatial equation x double prime minus px equals to 0 becomes x double prime plus lambda x square x equals to 0. This gives complex roots m equals to plus or minus lambda I. So the general solution is xx equals to a cos lambda x plus b sin lambda x. By applying the boundary condition, x0 equals to 0 gives a is equals to 0, leaving us with xx equals to b sin lambda x. And then applying the x, the t equals to 0, since b cannot be 0, we need sin 30 lambda equals to 0, which means 30 lambda is equals to n pi. So lambda n equals to n pi over 30 and x equals to bn sin n pi over 30. For the time equation, substituting p equals to negative lambda square into t double prime minus 9pt equals to 0 gives t double prime plus lambda square t equals to 0. The roots are m equals to plus or minus 3 lambda I, so t and t equals to c n cos and pi t over 10 plus dn sin and pi t over 10. Since the string is released from the rest, ut x0 equals to 0, which forces d n equals to 0. So tnt equals to cn cos n pi t over 10. Then uxt equals to xn times tn, and sum over all n, uxt equals to sum from n equal to 1 infinity of bn sine and pi x over t times cn cos and pi t over 10. So we combine the constant b, n and cn into a single coefficient an. So ux t equals to sum from n equals to 1 to infinity of an sine n pi x over t cos n pi t over 10. So to find an, we need to apply the initial displacement condition at t equals to 0. ux0 must equals to fx, which is the triangular shape of the strings. By setting t equals to 0 in our solution, cos of 0 equals to 1. So ux0 equals to sum of an sine n pi x over 30 equals to fx. This is a Fourier sine series. The coefficient are an equals to 2 over 30 integral from 0 to 30 of fx sine n pi x over 30 dx. And then we got 1 over 15 integral from 0 to 10 of 0.3x sine and pi x over 30 dx plus integral from 10 to 30 of 4.5 minus 0.15x sine n pi x over 30 dx. Then we use tabular method to solve the integration by part. After applying integration by part, we to both integrals and evaluating the limits, the two results combine to give an over an equals to 27 over n pi square times sine n pi over 3. Therefore, the general solution is uxt equals to sum from n equals to 1 to infinity of 27 over n pi squared times sine n pi over 3 times sine n pi of n pi x over 30 times cos n pi t over 10. For part C, we estimate U15 5 using the first three non-zero terms by substituting x equals to 15 and t equals to 5. So U15 5 equals to sum of an times sine n pi over 2 times cos n pi over 2. For the terms 1, we substitute n equals to 1 and we got negative 0.483 meter. For the term 2, we substitute n equals to 2 and we got 0.241 meter. And for the term 3, we substitute n equals to 4. So terms 3 equals to 0.027 meter. By adding all these three terms, we got U15 5 approximating equals to 0. Therefore, at t equals to 5 seconds, the displacement at the midpoint is approximately 0. The string is passing through its equilibrium position.